This video contains the solutions to the practice problems on multivariable maximum and minimum problems. For this first one, we're asked to find the critical points of this function. Now remember that the critical points are where the two partial derivatives with respect to x and y both equal 0, or in other words, where the gradient equals the 0 vector. So first let's find formulas for the two partial derivatives. So f sub x is going to be 2x minus 6, and then f sub y is 2y plus 8. So now we want to set both of these equal to 0 and solve. This time it's relatively easy because each of these equations can be solved individually. Solving the first one gives me x equals 3, and solving the second one gives me y equals negative 4. So that means the point at which both derivatives equal 0 would be 3 comma negative 4. And that's the only solution that we get, so that's the only critical point we find. For this next one, very similar problem, we want to find the critical points, but this time solving the two equations that we get will be a little bit more complicated. So again, the first step is to find the actual formulas for our partial derivatives. Derivative of x squared is 2x, derivative of xy is y, the derivative of 2x is 2, the derivative of y and 1 are both 0. And then for f sub y, the derivative of x squared is 0, the derivative of xy is x, the derivative of 2x is 0, the derivative of y is 1, and the derivative of 1 is 0. So we get 2x plus y minus 2, that has to equal 0, and then x minus 1, that has to equal 0. So it's easier to solve that second equation first. So x minus 1 equals 0 tells us that x equals 1. And now we're going to take that solution and plug it into the first equation. Since x equals 1, that means we've got 2 times 1 plus y minus 2 equals 0, which means that y equals 0. And again, that's the only solution that we get, so the critical point that we find is 1 comma 0. Now we have a more complicated problem. Now, not only do we need to find the critical points, we need to now test those critical points using the second derivative test to figure out whether each of those critical points is a local max, a local min, or a saddle point. So first things first, let's find the critical points. So once again, we find our two partial derivatives. F sub x is going to be 4x cubed minus 16y, and then f sub y is going to be 4y cubed minus 16x. When we set those both equal to 0, there's not really an easy way to proceed here. So let's start by solving the first equation for y. So pick an equation, solve it for one of your variables, and then the plan is going to be to take that solution, substitute it into the other equation. So when we do that, we get 4x cubed equals 16y, which means y equals 1/4 x cubed. Plugging that into my other equation is going to give me 4 times 1/4 x cubed minus 16x equals 0. So that's going to be 1/16 x to the 9th minus 16x equals 0. Let's go ahead and multiply both sides by 16, so we get x to the 9th minus 256x equals 0. Now, how in the world are we going to solve an equation with a 9th power in it? Well, we'll start by factoring. We can start by factoring out an x. We get x to the 8th minus 256 equals 0. And what we might notice is that x to the 8th minus 256 is a difference of two squares. X to the 8th is x to the 4th squared, and 256 is 16 squared. So we can factor again. We get x times x to the 4th minus 16, and x to the 4th plus 16. Now, x to the 4th plus 16, that's going to have no solutions. If we try to set this equal to 0, this is always positive, because x to the 4th, being an even power, is always positive, and then we're adding 16, so that's got to be always positive. But x to the 4th minus 16 is again a difference of two squares. That's x squared squared, and 16 is 4 squared. So that's going to give us x squared minus 4, x squared plus 4, times x to the 4th plus 16. X squared plus 4 doesn't factor because, again, x squared is always positive, and then 4 makes it even more positive. But x squared minus 4 is again a difference of two squares. So we get x minus 2 times x plus 2 times x squared plus 4 times x to the 4th plus 16. Phew! So after all that, we've got it factored, and we get three solutions: x equals 0, x equals negative 2, x equals 2, and then x equals negative 2. So those are our three x values for our three critical points. Now we need to find our three y values. So what we knew was that y had to equal 1/4 x cubed for us to have a critical point, and we also got three x values, 0, 2, and negative 2. So we're going to plug those all into our expression. So when x equals 0, y is going to be 1/4 times 0 cubed, which is 0. So that gives us a critical point 0, 0. When x equals 2, y equals 1/4 times 2 cubed, which is going to be 2. So that gives us a critical point 2, 2. And when x equals -2, y is going to equal 1/4 times -2 cubed, which is -2. So we have 3 critical points, 0, 0, 2, 2, and -2, -2. But now to actually use our second derivative test, we need to compute this number d, where d is f(xx) times f(yy) minus f(xy) squared. And as we recall from the previous slide, fx is 4x cubed minus 16y, and fy is 4y cubed minus 16x. So that means that fxx, the x partial derivative of the x partial derivative, is going to be 12x squared. Fyy, the y partial derivative of the y partial derivative, is going to be 12y squared. And then fxy is just going to be -16. So when we figure out our d, we get 12x squared times 12y squared minus -16 squared. And now we just have to plug our values of our different variables in there at our critical points and see what we get. So when we plug in 0, 0, d is going to work out to be, that's just going to be a big 0, minus -16 squared, that's going to be -256. And we know from our second derivative test that when we get a negative value of d, that means that we have a saddle point. So at 0, 0, that critical point is a saddle point. Let's look at 2, 2. When we plug in d, we get 12 times 2 squared times 12 times 2 squared minus -16 squared is again -256. And that works out to be positive 2048. Now when d turns out to be positive, we've got a little bit more work to do. We need to also look at the sign of f(x). Now remember, f(x) was this first value here. That's fxx at this critical point. That's 12 times 2 squared, that's 48. And 48 is positive. So since d was positive and fxx was positive, that means that this is a local minimum. And then similarly, when we go to the point -2, -2, it's going to work out the same way. D is going to work out to be 2048. You should work that out on your own and make sure that you agree with that. And then fxx is also again going to be positive 48. And so again, we're going to get a local minimum. So we had 3 critical points, 1 was a saddle point, and 2 were local minimums. Okay, again, same kind of problem, going to approach it the same way. This one's going to work out to be slightly less nasty, I think. So again, first things first, we've got to find our critical points. So we take our x partial derivative, that gives us x squared minus 3y, and then our y partial derivative works out to be y squared minus 3x. Again, it's not easy to solve these to set these equal to 0, but then we set them equal to 0 and solve. This first one's going to give us y equals 1/3 x squared. Substitute that into our other equation. That gives us 1/3 x squared squared minus 3x equals 0. That's going to be 1/9 x to the 4th minus 3x. Multiply both sides by 9 gives us x to the 4th minus 27x. This factors x times x cubed minus 27. And then we can use our formula for the difference of 2 cubes to factor that as x minus 3 times x squared plus 3x plus 9. X squared plus 3x plus 9 doesn't equal 0. That turns out to always be positive. And so we get 2 solutions, x equals 0 and x equals 3. Plugging back into our expression for y, when x equals 0, we get y equals 1/3 times 0 squared, which is 0. So that gives us a critical point 0, 0. When x equals 3, that gives us a critical point where y equals 1/3 times 3 squared, which is 3. And so we get the point 3, 3. So here we've got 2 critical points. And again, to test those critical points, we need to figure out d, which is fxx times fyy minus fxy squared. Fxx, since fx is x squared minus 3y, fxx is 2x. Similarly, fyy turns out to be 2y, and fxy turns out to be minus 3. So at the point 0, 0, I get d equals fxx, that's going to be 2 times 0, times fyy, that's 2 times 0, minus fxy squared, that's negative 9. Since that's negative, this is a saddle point. At the point 3, 3, we get d equals 2 times 3 times 2 times 3 minus negative 3 squared. That works out to be 27. That's positive, which means we need to look at fxx, which again is right here. fxx is positive 6, so since d was positive and fxx was positive, this is a local minimum. So this time we got 2 critical points, one was a saddle point, one was a local minimum. All right, last one here, we've got xy times e to the minus x minus 2y, and again, find the critical points and then test them to see if you have a local max or a local min or a saddle point. So first things first, got to find our partial derivatives. This time we're going to need the product rule. So if I think of my two functions as xy and then e to the minus x minus 2y, my product rule tells me that it's the derivative of the first function, which in this case is going to be y, times the second function, which is e to the minus x minus 2y, plus the first function, times the derivative of the second function, which is e to the minus x minus 2y, times the derivative of the thing inside, which is negative 1. And then fy is going to be similarly x times e to the minus x minus 2y, plus xy times e to the minus x minus 2y, and this time when I use the chain rule, the derivative of the inside is minus 2. Okay, so how in the world are we going to be able to set these equal to 0 and get anything out of it? This looks horribly complicated. Well, it turns out to be not so bad, because I can factor the left-hand side. Let's start with the first equation here. I can factor the left-hand side. I can factor out an e to the minus x minus 2y, and I can also factor out a y. And when I do that, I get 1 minus x. And so I've got 3 things multiplied together equaling 0. And that means that I've got 2 possibilities. So I've got 3 possibilities, one for each factor. But this first one can't be 0. I can never raise e to a power and get 0. So that's not equal to 0. So I really only have 2 possibilities. Either y equals 0, or 1 minus x equals 0, which gives me 2 possibilities. Y equals 0, or x equals 1. And both of those are possible. So now let's go to the other equation. So again, I can factor out an e to the minus x minus 2y. I can also factor out an x, and that gives me 1 minus 2y when I factor those out. Again, because I've got 3 things multiplied together equaling 0, this first expression with the e can't be 0, but I could get that x equals 0 or that 1 minus 2y equals 0. Which in other words would tell me that y equals 1/2. So now let's figure out how to put this all together. My first solution, telling me that y equals 0 or x equals 1, means that I have at least 2 possible solutions here, where x equals 1 and the y could be something else, something mysterious. And then another possibility is where the x is something mysterious and the y is 0. So those are the 2 possibilities that I have to have for my first expression. My point has to look like one of those 2 things, otherwise it's not going to be a critical point. And now in the second place, I know that x has to be 0 or y has to be 1/2. Well, if I'm looking at the first possible point, if x is already 1, then x can't be 0, and so the only possibility is that y has to equal 1/2. So that gives me a critical point 1, 1/2. In the second place, if I already know that my y equals 0, then y can't equal 1/2, and so the only possibility is that the x value has to be 0. So that gives me true critical points 1, 1/2 and 0, 0. And now we have to use the d-test to test these 2 critical points. So these were our first partial derivatives, f sub x and f sub y. To figure out d, we need to know fxx, fxy, and fyy. So to find fxx, we need to find the x partial derivative of this first derivative. Now the y factor is just a constant multiple, so that's going to stick around while I take the partial derivative with respect to x. So this is my first function, and this is my second function. So the product rule says that it's the derivative of the first function e to the minus x minus 2y times the derivative of the inside, which is negative 1, multiplied by the second function, plus the first function, multiplied by the derivative of the second function, which is just negative 1. And then fyy is going to be similarly, the x will be a constant multiple, and then I'm going to have a first and second function, which are these two. There's my first function, there's my second function. My product rule says that it's the derivative of the first function, e to the minus x minus 2y, times the derivative of the inside, which is minus 2, times the second function, plus the first function, e to the minus x minus 2y, times the derivative of the second function, which is negative 2. And then finally for fxy, I've got to either take the x partial of the y partial or the y partial of the x partial. So I'll just take the x partial of the y partial. So since I'm taking the x partial, this 1 plus 2y, that's a constant, and then these will be my first and second functions. Again, I'll need the product rule. So the derivative is going to be that constant multiple, multiplied by the derivative of the first function, which is e to the minus x minus 2y. Remember, I'm taking the derivative with respect to x, so the derivative of the inside is minus 1, multiplied by the second function, plus the first function times the derivative of the second function. Remember, the second function is x this time, and the derivative of x is 1. So those are my three partial derivatives. Now what I have to do is plug in the two critical points, 1 comma 1/2 and 0 comma 0. So let's start with 0 comma 0 because that's a little bit easier to plug in. So remember, d is going to be fxx times fyy minus fxy squared. And when I look at fxx and fyy, notice that there's a y and an x sitting out front of each of those. So if I'm plugging in 0 comma 0, both of those are just going to be zeros. All that crazy stuff inside the brackets, none of that matters because I'm multiplying all that stuff by 0. And then for fxy, now I actually have to plug in the zeros. And when I plug all that stuff in carefully, what I get is 1. And so my d turns out to be negative 1. That's negative, which means I have a saddle point. And then for 1 comma 1/2, again, I just have to be really careful to plug all this stuff in. fxx times fyy minus fxy squared. And when I do all this, fxx turns out to be minus 1/2 e to the minus 2. fyy turns out to be minus 2 e to the minus 2. And then fxy, in this case, turns out to be 0. So that's going to be minus 1/2 times minus 2 is 1, so that just turns out to be e to the minus 4, which is positive. Remember, that just means 1 over e to the 4th. And since that's positive, we look at fxx. fxx is right here, which is negative. So d was positive, but fxx was negative, which means we have a local maximum. So for this function, we have two critical points, 0, 0, which is the saddle point, and 1 comma 1/2, which is the local max.